Friends, in my first lecture, I have already given you theoretical explanation of all the concepts of sets. But it will be inadequate if I do not give you examples. So certain examples from your NCERT book I have selected, and I am just giving you the solutions to these problems. That doesn't mean it completes, because the remaining problems are to be solved by you people. And if you have any doubts, please send it to me. Okay. Now I have selected this particular problem, which is very interesting. This problem says that which of the following statements are incorrect. Basically, this problem deals with the concept of subset. So what is a subset? Let us look at the concept of subset. Once again, subset. Okay. Now, what is a subset? A set A is called subset of another set B if all the elements of A are in B. Every element of A must be in B. Then we say that the set of A is a subset of B. So that means we symbolically will write it like this. A is a subset of B. This is equivalent to x less than or equal to. It may be equal, it may be. But right now we are only ensuring that elements of A are in B. Maybe all the elements of B are also in A. But if that is the case, then equality will prevail. Otherwise, if there is one element in B which is not in A, then it will be a strict subset. So this is called strict subset if it is like this. Now, in order to be able to write this, I must ensure that all the elements of A are in B and there is an element in B which is extra, which is not in A. Then it will be strict inequality. Otherwise, it will be less than or equal to. When I am not sure whether there exists any element in B which is not in A, then I will be writing this. So if I prove that all elements of A are in B, I must write this. Okay. But if I prove that all elements of A are in B, but B contains one extra element than A, then I can write this. Okay. So in general, if I prove this statement, then I'll use this particular symbol. Okay. So now let us look at this concept. Now you will see there is one very strange way the set A is constructed. So look at A. A is constructed like this. It is 1. First element is 1. Second element is 2. And third element itself is a set. The element itself is a set, remember. So set, this is itself is a set, but this is now an element. Together it is an element, right? And then it comes what? 5. So this is the peculiar set where these are numbers as elements and one set itself is an element. Okay. So now I want to find out whether the statements are true, which statements are incorrect. Now look at this statement. 3, 4. 3, 4. 3, 4 is a subset of A. Is this statement correct? That means this has to be a set, not an element. If element belongs to a set, then we have a symbol like this, right? So what is this? This is set or element. As far as A is concerned, this is an element, right? So if element cannot be a subset of a set, so this statement is incorrect. I repeat again, why this set statement is incorrect? Because this is not a set. As far as A is concerned, this is just an element. And element is not a subset, okay? Element is contained. So if I say like this, 3, 4, belongs to A, then it will be correct. this is an incorrect statement, this is a correct statement. Okay. Now, in other words, this is a correct statement. Correct. So the second is correct. Second is correct. Correct. Look at the third statement. Third statement is what? Very interesting. Third statement is saying like this. A set containing an element called a set 3, 4. Now this is a set because it is enclosed in a curly bracket, and in a curly bracket one element of this set is included. So this is actually a singleton set. Why it is called singleton set? Because it contains only one element from A, and now I am making it a set because outside also there is a curly bracket. So this is a subset of A. The statement is correct. The statement is correct. Third statement is correct. Now look at the fourth statement. Fourth statement says that the number 1 belongs to A. This is the fourth statement. Is it a correct statement? Obviously it's a correct statement because 1 is a member of A. So 1 is an element inside A. So 1 belongs to A is correct. Okay. Now let us look at the sixth statement. The sixth statement says what? 1, 2, 5 is a subset of A. Is a subset of A. Yes. Every element of this set, this is a set because it is enclosed in a curly bracket, and this set contains 3 elements, 1, 2, 3, and this in itself is a set, but this set contains all the elements which are already there in A. So 1 belongs to A, 2 belongs to A, 5 belongs to A. Statement is correct. Correct. Next, VII, that is seventh statement. Okay. Seventh statement is 1, 2, 5 belongs to A. It's a repetition of the same statement, so forget about it. 1, 2, 3 is a subset of A. 1, 2, 3 is a subset of A. Is it a correct statement? 1, 2, 3 is a subset of A. Is this correct statement? Just look at it. Actually, 1 is an element of A, no problem. 2 is also an element of A, no problem. But 3 is not an element of A. 3 is not an element of A because 3 belongs to another set called 3, 4, and 3 cannot be an element of A. It is an element of what? This particular set. So this statement is incorrect. Because 3 is not an element of A, right? There is a set called 3, 4, which is an element, okay? So if I say 3 belongs to the set 3, 4, that's a correct statement, but not this one, okay? So let us go for this is again I'm so sorry, this is 8th statement. And 9th statement is what? 9th statement is phi, that is empty set, belongs to A. Again wrong. A set cannot belong to another set. Only element belongs to another set. So statement is incorrect. Okay. Now look at the next statement. 10th statement is what? That phi is subset of A. Yeah, yes, phi is a subset. And any empty set is always a subset of A. Why? Because you cannot find out any element of A which is not in phi. Correct? So you cannot find out any element of every element of phi is in A because there is no element of A and there is no element in phi. So it is considered to be a subset of all possible sets. So phi is always a subset of every set in the world. Okay. Now the next statement is again, look at it carefully. It says that this phi is a subset of A. Now remember one thing, that this is a set and this set contains an element called empty set. Now here empty set, this is not an empty set. This set is a set which contains one element called phi. So therefore this is not a subset of A because phi does not belong to A. Phi does not belong to A. Phi is a subset of A. Phi is a subset of A. Phi does not belong to A. Therefore, this statement is incorrect. Now, let us find out this kind of a problem, which says that write down all the subsets of the following sets. Okay. All the subsets, when we talk about all the subsets, one thing has to be considered, that empty set is considered to be a subset of every set. Okay. Because why empty set is a subset of every set? That's a very interesting question. Why we understand that phi is always a subset of A? Because I cannot prove the other way around. That means I cannot prove that phi is not a subset of A. I cannot prove phi is not a subset of A. Why? Because I cannot find out any element in phi which is not in A. That means I cannot prove phi is not a subset of A. That means it is not that phi is not a subset of A. Double not means what? Phi has to be a subset of A. So we are forced to accept the fact that phi is a subset of A. Because if phi is not a subset of A, I will have to create an element in phi which is not in A, which is impossible. So phi is always a subset of A. That means all these sets have one subset that is called phi. Okay. So let us take a singleton set. That is the first. Okay. Singleton set. How many subsets it has? One is empty set itself, as I said clearly. So empty set is a subset of A. Then singleton A, that means every set is always a subset of A. That is called improper set, right? So improper means what? This is a set which is a subset of this, because all elements of this set are in this. Therefore, this is also a subset of it. So how many subsets? This set has 2. So it has got 2 subsets. Okay. Now let us go for the second question. Second question is very simple. It contains 2 elements. Okay. Now how many subsets it will have? As I said first, that empty set is always a subset of every set. So therefore it will always come first. Then let us take out all singleton sets. So singleton A is a subset of A. Singleton B is also a subset of itself, right? And as I said, the whole set itself can be considered as a subset of itself. That means now this set has got 4 subsets. 4 subsets. It has got 4 subsets. Now, let us have a look at third example. What is the third example? Third example contains 3 elements. 1, 2, 3. Now, it will contain, obviously, it has a subset called phi. Then let us take all singleton sets. That is, singleton A is a subset of A. Singleton B is also its subset. Singleton C is also its subset. Then let us take all doubleton sets. AB is also a subset. AC is also a subset. And CB is also a subset. Correct? And then one last is the set itself. A, B, C. It is also a subset of set. Now can you make out how many sets we have? 1, 2, 3, 4, 5, 6, 7, 8. So here we have got 8 subsets. 8 subsets. Now can you make out? First set contained only one element. It has got 2 subsets. Second set contains 2 elements. It has got 4 subsets. Third contains 3 elements. It has got 8. So you can see the connection that this is 2 raised to 1. And 4 means what? 2 raised to 2. And 8 means what? 2 raised to 3. So it's very clear that every set containing n elements has got 2 raised to n subsets. 2 raised to n, because this set has 3 elements, it has got 2 raised to 3 subsets. This set has got 2 elements, it has got 2 raised to 2 subsets. And this set has got 1 element, it has got 2 subsets. Now, how many subsets empty set has? Empty set has only one subset, and that is itself. So phi has only one subset, and that is itself. Why is it so? Because it contains how many elements? 0. So how many subsets it should have? 2 raised to 0, and anything raised to 0 is 1. So this example gives you an illustration or a statement we can generalize, which says that if a set A contains if a set A contains n elements, then it has 2 raised to n subsets. Correct? So this statement has to be observed. Okay? So that is the lesson that we learn from this particular problem. Let us take another example, and this concept deals with a concept of interval. This problem deals with the concept of interval. So what is an interval? Interval means just imagine a real line which generally indicated by this, and at the middle of it there is a number called 0, and there are some numbers here, real numbers, there are some real numbers. You know, between two numbers, between A and B, how many real numbers are there? Infinitely many. Between any two numbers, there are always numbers. There are any two numbers, there are always numbers. We are talking about real numbers, because in all these sets you will realize they have written R, and we talk about real numbers here. Now, these real numbers are, and if I take a cut, or if I make a cut here, and cut here, then what is left is this line segment. This line segment is called an interval. What is this line segment? Consists of all the elements from A to B. So if I say A less than X less than B, then I'm talking about all real numbers X which are between A and B. This kind of a set is called open set. Open set, or it is called open interval. Open interval. Why it is called interval? Because no element between A and B is skipped. It is not excluded at all. Every element between A and B is included in this. That is why it's called open interval. Now, why it is called open? Open is because the boundary is not included. The boundary element here is A and boundary element here is B. So those elements are not included. That is why it is called open interval. But if I include them, that means like this, then it is called closed interval. It is called closed interval. Again, remember, it is called interval because every number from A to B, every real number has to be there, and even A and B has to be there. So boundary elements has to be there inside. Now, if I have a set like this, A, that means left hand element is included, right hand element is not included. That means it is called semi-closed or semi-open interval. Up to you. So one end is closed, one end is not closed, right? And another is, this is A less than or equal to B. This can also be a semi-open or semi-closed interval. Okay. Now, what are the notations for this? Notation is very simple. If the interval is open, then enclose it in a round bracket. So we say AB. That's all. That means all the elements from A to B. Now here in this case we call it a square bracket. Enclose it in a square bracket. So this is a closed interval, and this is a semi-closed or semi-open interval. So the end which is included will be square and the end which is not included is round. So it's like this, and this will be A and B. These are all intervals. Okay. So now, given the example here, you can clearly see the first. What is the first example? First example is X belongs to the set of real numbers such that -4 is less than X is less than or equal to 6. That means one boundary not included, another boundary included. So here the set will be open and here the set will be closed. So this is a semi-closed interval. Now look at the second statement. Second statement again contains all real numbers such that minus 12 is less than x is less than minus 10. Remember, there is no equality sign here. That means both the ends are not included. So it's an open interval from minus 12 to minus 10. Okay. Third, what is it? Again, it's a set of real numbers. Therefore, it is interval, right? Now, what kind of interval is this? In the third set, the left-hand element is included, right-hand element is not included. That means it's a semi-open or semi-closed interval where 0 end has to be closed and 7 end has to be left open. Okay. Whereas the last set is less than or equal to. So the last example contains this. It should be denoted by 3, 4. Okay. So that is how these no intervals are to be noted. Okay. Friends, I have selected this problem because I want to illustrate one very, very important law in the set theory. And that said, these laws are called De Morgan's laws. De Morgan's laws. De Morgan's laws are very interesting. If I want to write them in short, then I'll say complement complement of union is intersection of complements. Very interesting. What does that mean? That means if I take complement of what? A union B. So complement of union is equal to intersection of complements. That means A complement and B complement. Okay. Now these words are interchangeable. In place of union, I can write intersection. And here, instead of intersection, I can write union. That means, now what is the new statement? Complement of intersection is union of complements. That means whenever you take complement of any operation, union or intersection, you have to reverse it and take their individual complements. Okay. So these are the two statements which we are supposed to verify. Now here the universal set is already declared to be all the elements from 1 to n. Now what is A? A is this. Let us say A. A contains what? A contains 2, 4, 6, 8. 2, 4, 6 and 8. Now what is A complement? A complement means those elements which are not in A but which are in universal set. So elements which are not in A but they are in the universal set. 2 is there, 4 is there, right? So which are the elements which are not in A, which are in the universal set? For example, 1. So 1 is included here because 1 is not in A. 2 is there, 3 is not there, so 3, right? 4 is there, 5 is not there, so 5 I'll include here. 6 is there, 7 not here, so therefore 7 is included. 8 is here, 9 is not there, so 9 is not there. So A dash means A complement contains all the elements in universal set which are not in A. So this is A dash. Okay. Now let us write B. What is B? B contains elements 2, 3, 5, 7. 2, 3, 5, 7. What is B dash? That means B complement. That means elements which are not in B but in the universal set. 1. Is it in B? No. So it must contains in B dash. 2. Is it in B? Yes. 3. Is it in B? Yes. 4. Is it in B? No. So 4 will be included here. Then 5. Is it included? Yes. 6. Not there. So 6. Then 7, is it in A, B? Yes, it is in B. So 7 is included, 8 is not there and 9 is not there. So 8 and 9 all are there in complements. Now, let us see what is A union B. What is A union B? All the elements from A and B. So, from A, I'll write all the elements in A first. 2, 4, 6 and 8. These are the elements in A. Now, 2 is already included, so I'm not going to rewrite it again. So, 3 is there, 5 is there and 7 is there. So, this is A union B. Now, what is A union B complement? A union B complement. A union B complement means elements which are in the universal set but not included here. For example, 1 is not included here, so 1 will come here. Now, 2 is in U, but it is here also. 3 is here also. 4 here also. 5 here also. 6 here. 7 here, right? 8 here. 9 is not there. Okay, so it's 9 here. Okay, so 1 and 9, these are the elements which are not in A union B. Now let us see what is A dash intersection B dash. That means we have got A dash here and we got B dash here. Which are the common elements in both of them? 1 is common between them. Yes, 1 is there, right? So 1 is common, 3 is not common, 5 is not common, 7 is not common, 9 is common. Absolutely. That means these two sets are equal. So we have verified the law that A union B complement is equal to A complement intersection B complement. So first statement we already verified. Now let us look at the second statement. Second statement is what? First of all, we have to find out what is A intersection B. What is A intersection B? What are the elements common in A and B? Right? So look at this A and look at this B. Which is common? 2 is common. Then 4 is not common. 6 is not common. 8 is not common. So the only common element in this is, what is it? 2. So 2 is the only common element here. Okay. Now, what is A intersection B complement? That means all the elements in the universal set which are not in A intersection B. And A intersection B contains only 2. So except 2, all the elements I will have to write here. So 1, 3, 4, 5, 6, 7, 8 and 9. Except 2, all the elements are there in the A intersection B complement. Okay. Now, let us see what happens to A complement union B complement. So A complement union B complement. So A complement is what? Let us see. What is A complement? Elements which are not in A. So 1 is not in A. 2 is in A. 3 is not in A. Then 4 is in A. Then 5 is not in A. Right? Then 6 is in A. 7 is not in A. 8 is in A. 9 is not in A. So it contains these elements. Union B dash. What is B dash? The elements which are not in B. So 1 is not in B. 2 is there. 3 is there. 4 is not there. 5 is there. 6 is not there. 7 is there. 8 is not there. And 9 is not there. Correct? Now if I combine all these elements together, what will I get? 1, which is included in both. Right? Then comes what? 3. Then comes what? 4. Then comes what? 5. Then comes 6, 7, 8, 9. Right? And what is this? 1, 3, 4, 5, 6, 7, 8, 9. 1, 3, 4, 5, 6, 7, 8, 9. It's not a coincidence. It's a law. Which law states that if you take complement of intersection, it results into union of its complements. Okay. So this law is verified. We have clearly verified that A intersection B dash is same as A dash union B dash. Okay. Now see, I want to prove that LHS is subset of RHS and simultaneously RHS is a subset of LHS. That means if X belongs to LHS, X also belongs to here. And if X belongs to this, then X belongs to A. So let us take LHS first. So LHS, what is LHS? A itself. So let X be an element from A. Correct? Now there are two possibilities. Then X belongs to A and X may belong to B, we do not know. And X belongs to B. Correct? In that or X belongs to A and X does not belong to B. Correct? Now the first statement means what? What does that mean? X belongs to A, right? Intersection B. Because there is a and here, right? X belongs to A, intersection X belongs to B. Or X belongs to A but does not belong to B. That means X belongs to A minus B. Correct? So that means X belongs to A minus B. So what does that mean? That means X belongs to A intersection or can be converted by union A minus B. Correct? Which is nothing but RHS. So X belongs to RHS. Correct? So this is the RHS. Now we'll go to the reverse way. Now reverse way is what? I want to take now LHS. I have already shown. So now I want to show RHS is a subset of LHS. That means left hand side, right hand side is a subset of RHS. So that means I'll have to take X belong to RHS. So let X belongs to what? A intersection B union A minus B. What does that mean? That means X belongs to either A intersection B or A minus B. That is the meaning of union. Okay. Now, okay. So X belongs to A intersection B union A below. So X is either here or here, right? That is what I have said. That is a clear meaning of what? Union. Okay. Now, if X belongs to A intersection B, what does that mean? Or X belongs to A minus B. So suppose X belongs to A intersection B, means X belongs to means this statement. X belongs to A intersection B, or X belongs to what? A minus B. Correct? Now what does first statement indicate? So first statement means X belongs to A and X belongs to B, or X belongs to A and X does not belong to B, right? So these are the two statements. These two statements are, I can group them like this, so it's very clear. So X belongs to A and X belongs to B, or X belongs to A and X does not belong to B. Now combine these two statements, what does that mean? If X belongs to B or X does not belong to B, it doesn't make any sense, right? So that means X belongs to what? A, correct? And which means A is a subset of what? RHS, that is A intersection B union A minus B is a subset of A. Correct? So clearly we have proved that RHS is now subset of LHS and LHS is equal to subset of RHS. Therefore, LHS is equal to RHS. Okay. Now let us go to the next part. Okay. What is the next part? So before that, I'll erase the whole thing. Okay. So next part. What is our next part? Okay. Next part is A union B minus A. Now let us see this by using diagram first. Okay. So this is a universal set. This is a universal set. Let us call it U or X, whatever. And this is A, and this is B. Now what is being said here? That A union B minus A. Now B minus A will be this set. B minus A will be this set. This is B minus A. Why? Because these are the elements which are in B, right? Which are not in A. So this is B minus A. Correct? So this is B minus A. Now what we are saying is B minus A union A. That means this is united with A. If I unite it with A, then it will be like this. I mean, I will have to combine whole thing, right? So this is A. And if I combine both of them, that means I am talking about all this set. So can you see now that this union itself, this total shaded part is nothing but A union B. That is exactly what I want to prove. Okay. So now this is the diagram. Okay. So let us keep this diagram here slightly like this. So we want to prove now A union B minus A is nothing but A union B. Now, I want to take help of an identity here, that what is B minus A? B minus A is actually equal to B intersection A complement. Okay. So I'm going to replace this B minus A by this identity. So that means A, so this implies that A union B intersection A complement. Okay. Now, this implies what? This implies, you know, there is a distributive law of union over intersection. That means what is the distributive law? A union B intersection C can be written as A union B intersection A union C. Correct? So I am taking use of the distributive law of union over intersection. That means this union will be distributed on both the sets. So this implies A union B, correct, intersection A union A dash, right? So A union B intersection A union A dash. But elements which are A and as well as the elements which are not in A, that makes the entire universal set. So this becomes what? A in union B intersection the universal set X, or you may call it U. But universal set is this whole rectangle. Now what is common between this and this? That is nothing but what? A union B. Finished. So we have already proved that this is equal to what? This. Okay. Note that we have learned two properties. One is called, distributive properties as they call it. Distributive property. Distributive properties. Property. This distributive property applies to union as well as intersection. What are these properties? The first one is like this: A union B intersection C. A union B intersection C. So A union B intersection C. So this is union and we want to open this bracket. But if I want to open this bracket, I will have to distribute, and that means provide union to both of them. And in the middle sign will be intersection. So the property says that this is equal to A union B intersection A union C. Okay. That means I have distributed union over intersection. Correct? Now, the second property, you can just reverse these signs. That means A intersection B union C. Now here intersection is being distributed on B and C. So A intersection B, union A intersection C. These are the two properties, and by using these two properties, these two statements can be proved very, very easily. So do you understand this? Now I'm going to remove this and let us see. Okay. So let us see. Let us talk about the first question. So what is the first question? First question is A union A union B, intersection B. You know, A union A intersection B. Now just apply the distributive property. What does that mean? That means A union A, right? Intersection A, A union A intersection A union B. Correct? Now A union A is nothing but what? A union A is nothing but A only. So this means A intersection A union B. Right? A intersection, see, A union A intersection A union B. Now A union A is nothing but A. So A intersection, now what does that mean? That means A intersection A, right? Union A intersection B. Correct? So what does that mean? A intersection A is A only. Correct? So union A intersection B, that means if X belongs to, this implies nothing but A union A intersection B. Correct? So that means X belongs to A or X belongs to A intersection B. That means X belongs to A union A and A intersection B. That means in either case X belongs to A. So therefore it is equal to what? A. Show that A intersection B equal to A intersection C need not imply B is equal to C. What does that mean? Suppose this is a universal set. Suppose this is a universal set. Okay? This is our universal set. Now, A intersection B is same as, so this is A. Okay? And this is B. So this is A. This is B. Okay? And the intersection part is this one. Right? This is the intersection part. Correct? So this is the intersection. Now, if this intersection is same as A intersection C. So, for example, A intersection C may be this kind of element, you know. A intersection B is same as A intersection C. So, suppose I create a set like this. Okay. So, this set is made up of this figure. You know, this is my set C. Now, A intersection B and A, this whole combination is made of this. Suppose I call it this part 1. This is 1. This is 2. This is 3. And this is 4. Okay. So, my A is made up of what? My A is made up of 1, 2. These are the two parts. That is A made up of. Now, B is made up of what? B is made up of 2 and 3. Correct? And C is made up of what? 2 and 4. Correct? So, C is made up of 2 and 4. So, what is A intersection B? A intersection B. So, I take a set called A, which is 1, 2, B, which contains 2, 3, and C, which contains 2, 4. So, what is A intersection B? So, what is A intersection B? A intersection B is nothing but 2. Okay. Now, what is B intersection C? B intersection C is nothing but what? 2. So, here A intersection B is equal to B intersection C. But does that mean B is equal to C? Right? But clearly B is not equal to C because there is an element in B which is not in C. For example, 3 is not in C. For example, 4 is not in B. Therefore, we have proved, correct, that the statement is true.